Firstly, hello everyone, thank you for coming. I'm here to talk to you about my final year project, which forms a component of a larger project which was initialised by Paul McCormack. And so our design brief was, the overall aim was to model and then optimally design an off-grid solar electric system. So it would look something like this. You've got a generator. You've got a generator. So you've got a generator here. You've got an energy input, I guess, the requirement. You've got a set of battery banks, and you've got the solar panel. And so what my component was about was modelling incremental 15-minute solar energy levels for a specific location over a whole year. So from this data, we can model the solar panel's energy output over a year and then optimally design other components of the system, which is what the other guys will be talking to you about today. So I'll give you a bit of a background on modelling solar radiance. So what exactly is solar radiance? It's the amount of power available from the sun in a square, on a square metre, so available to our solar panels. And we would like to model this irradiance for a specific location and over a certain period of, and over a certain period of time. So if we can do that over 365 days, that's a data set to model our other component variables of. And so this is an irradiance curve of Geraldton, a day in Geraldton, and this is compiled from 1 minute solar data. So that's something we'd like to plot for 360, we'd like to model for 365 days. So how do we go about modelling solar radiance? Well, we've got some pretty nice equations that we can utilise to model them. And this is the equation utilised by Moore, who wrote a journal article on suggested models to utilise when modelling irradiance. And so the model he suggested has some positives, so it's suitable for computer modelling of irradiance, which is what we need, and the data is easy to collect. So any standard solar measuring equipment utilised will be able to give us the result, give us the data we need. One of the negatives is the complicated algorithm for cloud coverage, which we worked on developing. And so all this equation is telling us is the irradiance at a certain point in time. And so we can calculate that by finding the zenith angle and a coefficient alpha. So we have this equation, and the zenith angle is fairly easy to calculate. It's we have very good models of calculating the zenith angle, and all the zenith angle is it specifies the orientation of the sun to and the orientation of the solar panel. So it factors all of those components in. And what it is actually measuring is the angle of incidence of direct radiation onto a horizontal solar panel. So the zenith angle, the solar panel is here, you've got this vertical, you've got a direct ray of radiation intersecting the solar panel. That would be our zenith angle. So once we've generated these zenith angles, we can work out the alpha coefficient. So the procedure we utilised. We know the equation for global irradiance at a point in time t. If we integrate the the irradiance over the whole day, we will get a total energy available over that whole day. And if we multiply that by the extraterrestrial radiation and the constant factor, if we equate this equation, it'll give us an alpha coefficient if we optimize the alpha coefficient to best fit this. And so all this equation is saying is the total energy available in a day is equal to the extraterrestrial radiation times a constant. And we can calculate the extraterrestrial radiation fairly accurately. Extraterrestrial radiation is the radiation from the sun before it interacts with our atmosphere for that given location. Obviously our A and B constants, our A and B constants, now we can find these, but they vary on location, and so that's where our data set comes in. The constants are termed Angstrom and Prescott coefficients, and this was developed in the early 20th century, where we related monthly average daily radiation to monthly average extraterrestrial radiation. So this is the data we're gathering, and this is the data where we can predict. And then we also compare the monthly average bright sunshine hours, which is the data that we have, compared to what we calculate theoretically the maximum sunshine hours. And then we just scatter plot every month, so that comparison, we get the regression analysis, and that will give us the A and B constants, the coefficients. This is the data set that we require. So for any location that we model, we need monthly average daily global insolation. So it's a mouthful, sorry, but it's averaging the energy available to us in a day for the entire month. And so for Geraldton, we've got, for the whole year, data generated for a good data sample. And the monthly average daily bright sunshine duration hours is the average sunshine, the average bright sunshine measured in a day over a whole month. Okay, so once we've got all these values, we can input this into our model, and we can generate these plots of irradiance over a day. And if we compare that to, for example, a day in Geraldton, we see it fits pretty nicely. And a point to note is the change in time, so the increments that we utilise are in 15-minute intervals. So our overall system is optimising on 15-minute interval increments. There's one important thing to note about this plot, and that is it's missing cloud coverage, so it's a nice smooth curve. And so now we want to be able to factor in that cloud coverage into our model. Okay, so when we want to factor in our cloud coverage, what we can do is we can take the global irradiance that we've calculated for the whole year, and we can break it down into two components, the diffuse component and the direct component. The direct component is the total power available from the sun directly to the solar panel, and the diffuse component of the irradiance is the radiation from the scattering of the radiation from the sun within the Earth's atmosphere. And so we can break those two components up. So we've got the diffuse and we've got the direct. And when we add them up, we get that total insolation curve that we saw before. Now, something very useful that we can utilise when we model the cloud coverage was a finding made by Paul and Harry Schubert. Sorry if I didn't pronounce that correctly. But what they found is, as a cloud crosses over a solar panel. And it has a bimodal characteristic, so that means as the cloud passes over, it will instantaneously cut off the energy being produced by the solar panel. And that's very useful because it means we can introduce our cloud increments. We can use increments to acknowledge those cloud coverage, duration. Sorry, let me say that again. We can use increments to represent cloud coverage. So we can take away a 15-minute increment from this direct component, and that will be modeling a cloud passing overhead. So now we need to ask ourselves, how many 15-minute increments do we need to remove? So this is something that we implemented. What we do is we have the data sample of average monthly bright sunshine hours. We take that away from the calculated theoretical maximum sunshine hours. We create a normal probability density function with that value as the average. And so for each day of a whole month, let me say that again. For a whole month, each day, the model will select a certain hour to take away from that model. Or put differently, how many increments of cloud cover to introduce into that model. And so we've got a spread over the whole month of different types of cloud coverage. And so once we've got that, we can finally find our results. So we've got the diffuse component here, we've got the direct component here. This is an example of the generated day. And then we sum those up and we'll find our model, which is plotting the static blue curve. And then you have the measured Geraldine data for that day. So to give you a comparison of what's happening between the days, these are 2 days in June. And you have a good fitting day and a poor fitting day. What's important to note here is that we're not so much interested in exactly matching these curves every day. We're interested in the overall model over the month. And I just wanted to compare that varying cloud coverage over the month. See, for December, you have less cloud coverage than you would with June, and that's the seasonal difference. So the predictability of the model on a monthly basis is fairly accurate. We utilize the 1 minute Geraldine, we utilize the 1 minute Geraldine Irradiance data set for the whole year. We integrated that to get 15-minute increments, and then we found the monthly average daily 15-minute irradiance for our measured data and for our model data, and they fit pretty well. This is January, this is April, July, and October. And we did a regressional analysis to see how well we are fitting with those curves, and we got a very good value. Okay, so estimates of cost of energy. So once we've got these 365 days, 15-minute simulated irradiance, we can input that further into the model, and that will optimize the rest of the setup, so the solar panels, etc. And so our model output for a 1.2 kilowatt diesel generator with 4 banks of batteries, utilizing a diesel cost of 1.54. For 2013, we can see the average total cost of diesel for the year, for the measured data, and for the data we've calculated. And we've obviously run our model a couple of times to see if we're getting the same output, which we were. Okay, so to conclude, we can predict the monthly average daily 15-minute irradiance fairly accurately. We can model an accurate simulation of 15-minute incremental solar irradiance over a year for Gerald. Possibly other locations. More research is needed into testing the model on various locations. And finally, future work we need to obviously evaluate the model for different climate types and locations. And we can also utilise different approximations for modelling the cloud distribution. So you and Jordan offer a good model which we would recommend maybe in future work to try and optimise with our model and see what kind of output we're getting with that. Okay, so thank you very much for listening. It was interesting. Any questions?
Yeah. Good timing.
Just a sort of comment on, you were mentioning the further work that could be done.
Yep.
In your work, you appear to have assumed that the clouds have always the same sort of transmission, that they basically reduce the radiation level to a certain percentage fixed.
Yeah.
And obviously, that's not quite reality. Clouds can have varying thickness and thereby influence the level of radiation, vary the level of radiation. I just wanted to mention that this assumption comes in from the linearity of the Angstrom-Prescott equation. However, that is actually has been shown not quite correct. And so if you were to include that relationship is nonlinear, that also brings in the variability of clouds to some extent. Just wanted to mention that.
Yeah, okay.
But anyway, that was good.
And to implement on that, our model is fairly rigorous in that if you would like to if there are models that you can overlay onto the model for generating different values of solar radiance produced by different cloud covers, you possibly could. That could be something we could look at in future years.
But it might not be so sensitive because after all the clouds, that's when the energy is low, and so an error there mightn't be so significant. Nevertheless.
If you did vary the cloud transmission about an average, would it still work out to give the same results? So if it was average, like wouldn't it, over a month, wouldn't it still average out to give the same results? Yeah,
our model is averaging out to give the same monthly average daily installation of the data that we're using to generate the simulation for the whole year. So you will be getting the same monthly average daily installation and the monthly average daily bright sunshine hours.
Yeah.
Any other questions? Yeah, maybe I can ask one. I didn't quite follow the model. What's the objective model? What are we trying to achieve?
Okay, so I'll go back.
It's not just a simulated irradiance curve.
So the whole model is factors in an off-grid setup. So you have the generator, you have the battery bank, and you have the solar panels. And we would like to optimize the system. So should we use one generator or should we use more? I mean, battery should we use? Dependent on the consumption of energy. And for us to know how much energy we need to generate from the generator, we need to be able to model how much insulation we have over that whole year.
It's not an irradiance distribution over a day. So you can know when you should.
It simulates a model, so it will create, it will model for 365 days. Every 15 minutes it will model how much irradiance there will be on your solar panel for 365 days, and then we can
use this information to
optimize the other variables of the off-grid setup.
Okay. Thanks.
Is it optimised in terms of minimising diesel use or cost?
For that kind of question, you should
I'll cover that.
You normally have a good backup.
yeah,
Very good. Okay, with that, maybe we thank our speakers.
Yeah. Does that change slide?
It doesn't change slide, yeah.
Yeah.
Such a boring
So the story